Okay, we'll begin, continue our discussion of radical chemistry. So we talked last time about various ways to initiate radical chemistry. Let's now talk about sort of propagation of radical, and we'll just use radical addition to olefins since addition is a theme of this chapter. So if you have an olefin that's not symmetrical, the radical will add to the olefin, and you tend to get the reaction such that the radical adds to the less substituted carbon. So we call that a propagation step because you're trading one radical for another. And then usually that radical that we just made, again, the regioselectivity here is governed by what makes radicals more stable. So the electron donating substituents, those methyl groups, by hyperconjugation stabilize the radical. Though again, as we said last time, radicals can be stabilized both by electron withdrawing groups and electron donating groups. So it gets a little bit tricky. After we have this radical, then remaining HBr can react with the radical, removing a hydrogen atom, or hydrogen atom abstraction is what that's called, to generate this product. And if you compare sort of these propagation steps from radical addition of HBr to an olefin, if you compare that to what you would have seen if you just did regular non-radical addition of HBr to an olefin, the position of the bromo group on the less substituted carbon and the hydrogen on the more substituted carbon is backwards from what you would get from just regular normal addition of HBr. So we call that anti-Markovnikov regioselectivity. Okay. Now, one of the things that makes people a little bit uncomfortable with radical reactions is just that there's a lot of different things that can happen. And your text sort of goes through what some of these are. The propagation step, the second propagation step, I guess both of these, but maybe the second propagation step is an example of what we call chain transfer. That is, the radical is being transferred from one propagating species to another. And of course, we can go through and do these two radical propagation steps in series, one after the other. And in the next step, this bromo radical is here and reacting with more olefin. We'll talk about the rate of chain transfer as KCT. And again, chain transfer means transfer of the radical from one propagating species to another molecule. And we'll contrast this with another possibility for a propagation step, which is polymerization. So we could ask, what if instead of this radical intermediate finding HBr, what if it finds additional olefin? And then the radical reaction would be addition of this new carbon-centered radical to the olefin to give you new bond. And basically, we haven't chain transferred. The radical is still part of the same molecule. The molecule has just gotten longer. Okay? So we'll call this a polymerization step. And we'll call the rate of that Kp for polymerization. So depending on how fast chain transfer is versus polymerization, you can get mixtures of products. Okay? Radical polymerization is a familiar reaction. It's how some plastics are made. So how can you think about sensibly whether or not you're going to get chain transfer to get a small molecule product versus polymerization to get this kind of larger polymer? So if your concentration of your HBr and concentration of olefin are similar, then we expect to see mostly small molecules when the rate of chain transfer is faster than the rate of polymerization, and then mostly polymers or short oligomers when polymerization is faster than chain transfer, and then sort of a mixture of polymers, small oligomers, and small molecules when chain transfer and polymerization are competitive. And it turns out that the chain transfer rate is related to how favorable it is to abstract a proton from HBr. So, for example, just based on bond dissociation enthalpies, abstracting a hydrogen atom from HCl is uphill by about 5 kilocalories per mole, whereas abstracting a hydrogen atom from HBr is downhill by about 10 kilocalories per mole. So what that tells you is that chain transfer for, because again, we're talking about how favorable this reaction is, this step 2 for chain transfer. So the rate of chain transfer for HCl is slower than for HBr. So we tend to see small molecules for HBr radical additions, whereas we tend to get oligomers for HCl. All right, so there is some rationale to help you sort of navigate what's going to happen, but it's related to how unfavorable or favorable this reaction is, this chain transfer reaction versus polymerization. Because again, notice in the chain transfer reaction, you're going from a carbon-centered radical to a bromine radical, whereas in polymerization, you're trading one carbon-centered radical for another. Okay. Questions or concerns there? Okay. Termination is how these reactions come to a close. Termination steps are relatively rare. You can terminate via what's called dimerization, where one radical finds another, and that could be two of the carbon-centered radicals. And so you make a small amount of, say, an undesired product. So that would be perhaps if two of these carbon-centered radicals found each other, then you would get some weird product that looked like this. But again, usually that's chain transfers, dimers or terminations relatively rare, and so hopefully, for the most part, you get your small molecule product. Another mechanism for radical termination that I didn't actually know about until I looked at the text is called I can't spell it. Disproportionation. This is where two radicals don't couple with each other, but they react with each other to give two different products. So here is a carbon-centered radical, and then here is another. And one disproportionation reaction would be for this carbon-centered radical to abstract that hydrogen atom, and then the remaining single electron after a hydrogen atom is removed goes to form a new pi bond here. So the two products you would get from disproportionation would be this olefin and then this molecule. Whether dimerization happens versus disproportionation happens is a function of temperature. Disproportionation is favored with increasing temperature, in part because the entropy of activation is lower for disproportionation. And remember that delta G equals delta H minus T delta S. So the impact of entropy gets, activation entropy gets higher at higher temperature. I don't know necessarily why both of these require two molecules to come together, but apparently the transition state needs to be more ordered when you have the two radicals reacting with each other to form a new sigma bond, versus this one where the two radical centers don't actually have to be that close to each other. Okay, so there's tons more about radical chemistry, but that's sort of a crash course. There's some more stuff in your text about regioselectivity and electron donating versus withdrawing groups, but it's pretty general and maybe not worth talking about. Yeah.
Okay, so we learned a little bit about this and something like that.
Yeah.
And something that I've always wondered is how you characterize polymers.
Okay.
If that's relevant at all. Because it seems like, sometimes you get small molecule and sometimes you'll just get these like infinitely long polymers and you get a lot of just byproducts. So like, how do polymer chemists like know what they're dealing with? You know what I mean?
Yeah. It's a good question. How do I get rid of the box of doom? We've never yet figured that out. That's really annoying. Anyway, okay. To answer your question, how do you characterize polymers? Well, So for this kind of radical polymerization, you would expect to get a mixture of lengths, right? And the mixture of lengths and molecular weights is called polydispersity.
Okay.
So, and there are a lot of ways to characterize polymer length. You could do a mass spec experiment, and what you might see is a series of peaks that look kind of like this, where you see a distribution of polymers.
Okay.
There are other experiments where you can measure size. Size exclusion chromatography is one of them. Dynamic light scattering is another. But in general, you do experiments and you see some distribution of size, and you get an average size there, which sort of tells you on average how long the polymer is. And then you get some standard deviation, which tells you the distribution of polymer lengths that you have. And there's this property called polydispersity. You can calculate it, and if polydispersity equals 1, I think that means it's monodispersed, meaning all the same length. If it's higher than that, that means it's more diverse.
So
Yeah.
they kind of have their own things to like find their lengths.
Uh-huh. Yeah, so you need some kind of analytical technique to assess the distribution of lengths. Now, yeah, and to some extent, you can control length. Imagine you're doing a polymerization reaction. You have a fixed amount of olefin starting material. You can control length to some extent by how much radical initiator you have per olefin starting material. So you can imagine if I start a lot of chains going, then eventually I'm going to run out of olefin fast, and so all of the chains are going to be shorter. If I only have a few radical chains initiated, then the polymers are going to be quite a bit longer. Yeah. There's whole classes that could be taught on polymer stuff, and I'm not an expert, so sort of.
It was like a materials class, but it might be too much information for what I want.
Yeah. Okay, what else? Okay, so while we're on the subject of weird kind of reactions, let's talk about carbenes. So the key issue for carbenes, and this is section 10.11. We're spending so many days on chapter 10. It's kind of a pain, but whatever. The key issue is that carbenes can exist in a couple of different electronic configurations. You've got singlet versus triplet carbenes. A singlet carbene is basically one in which the 2 electrons on the carbon are in the sigma out orbital, and the p orbital on the carbon is empty. And so you can, and the geometry for singlet carbene is bent. And we talked about this in our chapter on molecular orbital theory. If the carbene is bent, the sigma out orbital is quite a bit lower in energy than the empty p orbital, which explains why both of those electrons are in that sigma out orbital. In triplet carbene, these tend to still be somewhat bent, though their geometry is less bent than singlet carbene. In triplet carbene, the sigma out is singly occupied and the p orbital is singly occupied, and the geometry is closer to linear. Of course, if it's completely linear, actually this sigma out orbital just becomes another p orbital that's degenerate with this one. Reactivity of singlet carbines tends to be just typical 2-electron nucleophile electrophile. The sigma out orbital is nucleophilic, the empty p orbital is electrophilic. For triplet carbines, these tend to react like diradicals. And so both of them can do addition reactions to various molecules, including olefins, though the mechanism tends to be a little bit different. So, for example, I'll show you for both singlet and triplet carbines how you would draw the mechanism for addition to olefins. For singlet carbine, the mechanism is going to be mostly concerted. So here is how I would draw just the Lewis structure of a carbine. I would need to remember that there's an empty p orbital there. I would show the pi electrons attacking the empty p orbital and then the lone pair attacking the other carbon. The reaction is concerted and you end up making a cyclopropane. And because it's concerted, the reaction is stereospecific. That is, the stereochemistry on the olefin is going to be reflected in the cyclopropane product. For triplet carbine, in contrast, you're going to see a stepwise reaction because, again, triplet carbine, that's a terrible way to draw it. Maybe we won't draw it like that, but that was attempting to reflect the fact that triplet carbine has 2 unpaired electrons. We react one of them sort of via radical addition to olefins first to give you the following intermediate. And then in the next step, you close the ring. And there's time there for rotation around carbon-carbon bonds. And so because it's stepwise, the reaction's not going to be stereospecific. That is, you can lose some of the stereochemical information in the olefin, may or may not be reflected in the product. Okay. Another reaction that carbines can do is called CH insertion. So we'll maybe say just a little bit about that, though most of the examples, most of the chapter in your text about carbines is going to focus on the addition to olefins behavior. So for CH insertion for singlet carbine, what happens is basically you have the lone pair in the sigma out orbital attack this proton. At the same time, you're doing an elimination reaction, and these electrons go into the empty p orbital to give you this olefin product. Again, for singlet carbine, that reaction's concerted. For triplet carbine, CH insertion acts a little bit differently. Again, it's stepwise. First step is hydrogen abstraction. And then in the second step, you can get radical recombination. And this one looks, the product here looks perhaps a little bit more like a CH insertion, sorry. That's better. This sort of looks more like a CH insertion product. It's like we've inserted the carbene in between this hydrogen and the carbon of your original molecule. Again, for both of these CH insertion and addition to olefins, it's stepwise for carbenes, or sorry, for triplet carbenes. Okay. So we can talk a little bit about how to generate carbenes. This is kind of fun. It can be kind of tricky, and you do have to be careful because some of the reagents are dangerous. So one of the most famous ways to generate carbenes is with these so-called diazo compounds. And they're, sort of a pain to draw because you have to have formal charge on them. You can draw a resonance structure in which the negative charge is on this carbon. This is the one that it's easiest to see how carbene generation can happen, because you basically in these diazo compounds have a really, really great leaving group, which is nitrogen. If it up and leaves and bubbles off, then you're left with your carbene. If those two R groups are both hydrogen, the molecule is called diazomethane, and you need to be really careful with that. Diazomethane gets explosive when it gets in contact with ground glass joints. So you need special glassware to do any chemistry with diazomethane.
Wait, like normal round bottoms, it just explodes?
It's not, it's the ground glass. That surface causes the diazomethane, I think, to crystallize, and when it crystallizes, it's explosive.
That's fun.
So there was a reaction we did in grad school that involved diazomethane. You had to generate it in situ and distill it with a cold finger and drip it down into a reaction flask. And yeah, you had to have special joints that were not ground glass in order to avoid. You still did it behind a blast shield to avoid potential explosions. There are other ways to generate carbenes that we can talk about, though I don't know that they're that interesting or worth our time. Just trying to see what else we've got. I took detailed notes on the chapter, but not all of which is written in the chapter seems that interesting to me. So I guess one that you ought to be aware of, I think this is a reaction that's covered in like 351 or 352, but I often skip it. But it's famous enough that it's probably worth a little bit of your time. Simmons-Smith reagent basically generates a molecule that reacts like a carbene. They call it a carbenoid. And you'll sometimes hear people talk about the Simmons-Smith cyclopropanation. You ever heard of that? Vaguely? No? So the idea is you take diiodomethane and you use a combination of zinc and copper, and the zinc inserts between the carbon and the iodide bond, so you end up with which kind of reacts like a carbene because you have a leaving group here, and then here you have a pair of electrons. It's in a carbon metal bond, but if we're thinking of this like, if this looks actually not that different from like a Grignard reagent, right? Right, it's an organometallic reagent. We're sort of used to using reagents like that, where the electrons in the carbon metal bond are sort of like have carbanion-like character. So this reagent can do carbene-like cyclopropanation chemistry. So here's your olefin. Again, olefin attacks the carbon, leaving group leaves. That's one carbon-carbon bond, and then this is the other. And that generates your cyclopropane ring. Okay. So now that we've done sort of all of the addition reactions, the rest of the chapter is on elimination reactions. And some of these, your text sort of organizes these. Your text is going to talk about the traditional E1, E2, and E1CB reaction mechanisms, but I really spell very terribly when I'm talking. Elimination. But at least at the beginning, your text is going to focus on elimination reactions that generate carbonyl-like intermediates. So the first is acetal hydrolysis, which you may look at this and you're like, what does this have to do with elimination?
Dr. Bryce, is this chapter 11 now, or?
Nope, this is still 10. I've never really figured out how to get through these chapters in a reasonable amount of time, and this year I decided not to try to skip over stuff because I thought you'd be cheated otherwise, but it's just a long slog and I'm not sure. So this may or may not have been a good decision, who knows. Okay. Acetal hydrolysis you should have seen a gazillion times, so you tell me what I'm going to do. Okay, protonate. If this is prior to the rate determining step, what kind of catalysis do I have? Right, specific acid catalysis. All that means, in addition to the issues over, oh well, water is the hydronium is the acid and that is the specific acid. The idea is that if the protonation step happens prior to the rate determining step, it's specific acid catalysis. Okay, so then what? Sure, I mean water is the conjugate base of H3O+. What's my next step in acetal hydrolysis? Ultimately, my products are going to be ketone, alcohol.
One just leaves, right?
So which,
That just leaves.
the right side leaves? Okay. And this is the elimination step, right? You have, and it follows a pattern that if the carbon that has, all right, hold on. This is the leaving group, right? The carbon that has the leaving group is the alpha carbon. The beta atom is adjacent to that, and you got a lone pair on that beta position. Okay? When that happens, the lone pair can kick down to form a pi bond, the leaving group leaves. That's an example of a pattern called beta elimination. You've seen it in other forms. Another form of beta elimination is your classic E2 reaction where form a pi bond and the leaving group leaves. But again, the similarity between those two situations is you've got a leaving group on the alpha atom, and on the beta atom you either have a lone pair or you made a lone pair by removing the proton. Does that make sense? Okay. So that's a common pattern of reactivity, and that's why they're putting acetal hydrolysis in this section on elimination reactions. The intermediate thus generated is this oxocarbenium species, positively charged oxygen. By the way, this type of reaction is supported by O18 labeling experiments. There are some other alternatives that you might consider. What happens next?
Water attacks the carbon.
Yep. One of the alternatives would be, oh, well, what if instead of, what if we had water attack here? And if we did that and the water was O18 labeled, the final alcohol product should have O18 in it, but it doesn't. The oxygens from the alcohol are here, and those stay there and don't exchange with solvent, right? So yes, in the next step, water attacks the carbonyl carbon, tetrahedral intermediate. Okay, then what? Boring. Nope, it's fine. Okay, this is now a hemiacetal. Then what? Proton transfer. Which one am I going to protonate? The other one to turn it into a good leaving group. Okay, then what? Another beta elimination, right? Again, the pattern of alpha, beta, lone pair on the beta atom, leaving group on the alpha atom. That releases our alcohol. We get another oxocarbenium species, which in the final step we regenerate the acid to get the ketone shown. Okay. Specific acid catalysis, like I said, is the major, is what's thought to be the major issue behind acetal formation. Though, if you use better, if you change your alcohol such that so that the alcohol becomes a better leaving group, you can start to see some general acid catalysis. I'll give you an example of that in just a little bit. Some evidence for this mechanism comes from Hammett analysis. So if you use this acetal and change the various X groups here, and then measure the rates of reaction and plot the log of your observed rate constant versus your sigma values. The rho you end up with is minus 3.3. And that's, again, remember that that these sigma parameters were derived for the benzoic acid reaction, deprotonation reaction, where a buildup of negative charge was observed. If rho is positive, that means there's a buildup of negative charge in the transition state. If rho is negative, that means it's opposite the benzoic acid reaction, or there's a buildup of positive charge in the transition state of the rate determining step. And that provides evidence that probably, if you think about the intermediates in acetal hydrolysis, we protonate one of those alcohol groups, and then the elimination step is probably the rate determining step, and that involves buildup of positive charge. And of course, you could draw a resonance structure in which at least some of that positive charge is going to be on the carbon conjugated to the ring. So that Hammett analysis and the size, that the sort of large size of that rho value, provides some evidence that the rate determining step is this beta elimination. And then, as I said, if you use alcohol groups that are better leaving groups, there's some evidence that you can see general acid catalysis instead of specific acid catalysis. So here's kind of a custom example. Paranitrophenol is the leaving group, right? You can see if that left, it would be negatively charged, but it would be stabilized by resonance with this electron withdrawing group. And so there's evidence that proton transfer for this reaction happens during the beta elimination step. So that's to generate your carbenium intermediate, and then your paranitrophenolate leaving group, or rather your paranitrophenol leaving group. And you can do experiments to determine the extent of protonation. This value alpha tells you the extent of protonation in the rate determining step, and so there's about 50% protonation in the transition state here, which gives you again a sense that this is general acid catalysis. Okay. The next couple of reactions are related to elimination reactions, but they're different. They're going to follow this beta elimination trend or pattern, but they're not. They're going to be different from acetal hydrolysis. So one is the Jones oxidation. Have you heard of this before? I think this reaction you learned in 352. So in the Jones oxidation, your reagent is CrO3. This is a chromium-6 species. And what happens first, you run the reaction under strongly acidic conditions. So what happens first is one of your oxygens on chromium gets protonated by the strong acid. And then that generates this activated species. The arrow pushing we're going to do is sort of very analogous to acid catalyzed addition of an alcohol to a carbonyl group. So the alcohol attacks the chromium. You end up with this kind of intermediate. You remove the proton from the oxygen. And this intermediate is called the chromate ester. And then the next step is a beta elimination. Here the oxygen is alpha and the carbon atom is beta. And what you've got here, though it's not completely obvious, is a good leaving group. So in an E2 elimination type step, water removes the proton, electrons kick down, and then these electrons leave. This is the oxidation step because those electrons used to belong to our alcohol. They were on the oxygen, and now they leave with chromium. So that's the oxidation step. Our molecule is literally losing electrons. It's this beta elimination step that's the slow step, but that converts our secondary alcohol into a ketone. We generate H3O plus, and then the leaving group is a chromium 4 species. So we've gone from chromium 6 to chromium 4. Chromium gained 2 electrons. Our molecule lost 2 electrons. There are a number of variants on that sort of oxidation reaction, but that's a classic one. And again, the slow step is this so-called beta elimination. Does that look familiar? You've seen that before once? Okay. We're out of time, but what I want to show you next time is an analogous reaction. To do the Jones oxidation, you often use CrO3 and like sulfuric acid. It's not every run-of-the-mill organic molecule that can withstand sulfuric acid, so we need a lot more, a lot of other oxidation conditions. There are many of these. One of the most common is the Swern oxidation. Some of you may have done that before, but it's one that's pretty common. It also involves a beta elimination step, and I'll show that to you guys next time. We'll also talk about sort of E1 and E2 and E1CB eliminations, and I think that will take us through the end of chapter 10. All right, have a good Wednesday.